Good afternoon, New Orleans. I always wanted to say that. I'm going to talk to you today about Go and Ruby, and possibly little flying saucer symbols in the middle, but I think that bit will probably run out of time for. My name's Eleanor. I lurk all over the internet as Faye Eleanor, and I'm a dropped-out open source developer with a 2-year-old. So if anybody in this room is petrified of programming languages, especially low-level ones, I'm a stay-at-home mum and I can do them. So get over it. Well, here's a little bit about me. Some of the things lurking in here are song titles from very obscure bands, so I apologise for that. I also apologise for the fact that if your English is not your first language, I talk very, very fast when I get very, very nervous. And for everybody who hasn't got absolutely perfect 20/20 vision, there's a lot of code and it will all be too small. So, I've been hanging around in the Ruby world for about a decade now, and most of the stuff I like to play with is the sort of stuff that people don't normally think of for Ruby. Click. And this is the appropriate disclaimer. Click. So, okay, so I gave a talk earlier this year called Go, It's Not Just for Google. And I got a nice email from Bob Pike after he saw the video of it. He said, "You made me cry. We do want people to use our language." And I thought, well, fine, I will continue talking about it then. So this one should, yeah. Next one. I don't know if I'm going to get through any of what I want to get through today, but anyway. This is Gordon the Gopher. He's kind of cuter than Glenn the rabbit, but it's a whole Plan 9 sort of in-joke thing. And he lives at Google. He's got about 134 non-Google employees who have contributed to his codebase. He's fully open source, and he's a language that has a language spec that's being implemented, rather than a standardized committee that's trying to figure out what the spec should be. So this actually means the spec is readable and very short. Fire. This is a very simple example of a Go program. I have decided to set all of these slides going on half-second timers because they just show you what you should actually think about. I've got so many versions of this slide deck up, and it's probably the best documentation for how to learn to write Go programs if you're a Rubyist. But the more that I look at them, the less I can think of to say when I've got them going. So this is a very simple program. There's some constants and some variables and some printing, and it's all very unexciting. Fire away. You're getting work out. Go is a very small language, and I was going to dwell on both the keywords and the data types, but I'm not going to. We're going to skip that. So this is more useful to us, the comparison between Go and Ruby. People actually think, well, a lot of people who come from a dynamic languages background get petrified of statically typed languages, and also think that compiled languages are all going to be a pain like C++, etc. And Go is actually a very sweet little language that isn't really that different to Ruby once you get into it. Yeah. So first we're going to talk about type in Ruby, because then I'm going to talk about type in Go. And not enough people understand type in Ruby in the first place to understand type in other languages and how it can be like Ruby. So, yeah. Stupid little diagram demonstrates how most people think that type works in Ruby. Message comes in, hits instance, works up the class hierarchy, pulls in stuff from modules. Complete lie. Because for one thing, classes themselves are instances and can change. So if I drew this as it really is, I'd have branches all over the place, all with superclasses. So, an easy way of thinking about type in Ruby is to think, we have an instance class and an inherited class possibly, and we have an expressed type that's also comes from a set of modules that we can mix in. And this expressed type thing is actually going to be key to understanding type in Go. Fine. Here's a simple example of Ruby doing some of this type stuff. Class inherits from another class, a class, calling some superclass methods, all very unexciting. Fine. Last time I gave this talk was by Skype call to Lone Star. And off the top of my head, I just said, you know, Ruby type is like quantum mechanics. Because it is. The moment you blink, it's changed. Or as something more useful that came out last night talking to Edmund Phoenix, Ruby type is time variant. So you never actually know the type of an object, you just know that you're on the right time sequence for the object. I started off as a physicist, so I know things in weird ways. Fine. Now, Go's type system tries to solve all the problems that computer scientists perceive in the kind of type systems that we as Rubyers love. And it fails. So but it only fails if you happen to have spent 2 years making it perform strange experiments as a Rubyist. So to a Python programmer, you wouldn't go down this route, you wouldn't get there. So I like to refer to it with a TM and clearly defined areas of doubt and uncertainty, because they're very clearly defined. So far away. Yeah. All type in Go ultimately derives from a memory layout. Even things that don't actually have a memory layout, the compiler still insists on setting aside a byte for storage for them, which is actually really annoying when you want to create ineffable types that don't have any representation. I'm not going to say how to do that, but it's just the first hack I actually thought of when Go was released was, oh, can I create a struct type that has no storage? And according to language spec, you can, but then it takes a byte, which is very annoying because effectively that's a garbage collection problem, isn't it? So anyway, you've got a memory layout and you've got a method set, which is what we'd normally just call a bunch of methods on a class. And you've got a static type that's the combination of the two of those. But you've also got a thing called type embedded, where you can stick a struct type inside another struct type, which is the exact opposite of the way you do inheritance in C++. You don't, because you can't override the embedded type, you can only make it disappear, which is quite an interesting type system, by the way. This is a simple example of a type. You can, there are 13 base types in Go, and you can turn any one of them into a user type, just by declaring a type that uses that type as its memory layout. And then you can declare any old method you feel like on it. This is an example of declaring a method on a pointer, which means you can only use this method with pointers to that type. You can also declare it on the type itself, via. I think I might have got the wrong delay on that one.
There you go.
Right. This is a slightly more substantial example. This is actually creating a type that actually uses a slice of the previous type as its underlying memory layout. A slice is just basically an immutable array that lives in memory, that's got a little header that's a pointer to the array and some information about the length and capacity. So you can chop around the content of the array and shrink and grow the apparent array without having to reallocate the underlying memory or have to do any pointer math. None of this is particularly interesting. It's some code I've got lurking in the project. So next one. And this is an example of a program that just uses that and prints out some stuff. There are some bizarre little shortcuts built into Go. I mean, syntactically, I particularly like this one, because you can define either a bottom bound or a top bound for a slice that you're playing with. And then it will just do everything from 0 to the top bound, or from the bottom bound to the end of the slice, which takes away having to keep len whatever -1 to calculate what the actual index of the last thing in the slice is. Fire away. This is an example of using a struct to embed the previous type in another type. So a vector basically will take a buffer and then do some other stuff on top. It's not very exciting, but just shows the point. This is where we get into more interesting stuff. This is called an interface. An interface is just a method set. It says anything that's got this set of methods on it will comply with this interface. And then you can write loads of codes in terms of the interface, but you never specify that something implements that interface. Type inference takes care of that. And this thing here that's currently in red, this is what's called the blank interface. That's any type that has any method set at all, or no methods. So that matches all of the basic types as well, the built-in types. And we're going to meet that quite a lot later, because I'm going to go into how Go's reflection system works. Okay, next one. This is just an example of creating one instance of one type that actually complies with that interface. Next one. And this is another one that complies with the same interface. So one holds integers and the other holds floating point in a slice. Next slide. And this is an example of the fact that you only have to declare a variable as the interface type, and then you can use both of those types interchangeably in that and call the methods on them. So it starts to, it's basically you've started to get a reasonable duck typing, but a duck typing with a bounded type set. Next. The main point about this is computer scientists are a lot happier with Go's approach to duck typing than they are with Ruby's approach to duck typing. Because when you blink in Go, things don't change in the background without a lot of work. Whereas in Ruby, there's no guarantee they won't change in the background, by the way. This is actually constructed as a set of lightning talks because I've got so much stuff, I don't know how much of it I can actually get through. And, and I couldn't really think of what I wanted to cut. So I'm quite famous in the Ruby world for the fact I never write tests. I just use IRB. And for years and years and years, people thought I just hated testing. And I don't. I really love testing. It's just I like to do interactive testing. When I'm writing code in Go, I don't have an interactive mode. There's no equivalent of IRB. It's a compiled language. People are working on just-in-time recompilation to give you a sort of a faked way of doing it, but it's a clunky tool at present. So I tend to write unit tests, which is different. I actually enjoy it as well. That's the weird thing. Fire away. So we're going to start off. We're going to define something. In this case, I've defined an equals method on the buffers because I'm going to want to check in my tests whether two buffers are equal. Next. What you've got going on here is just a stupid little test. And Go's testing framework is, well, it's a testing tool, not a framework. It's called gotest. And you basically write a whole bunch of tests in a file, and they're marked out by having test as the first four letters of the function names. And it just compiles that up into a program and runs it. Now, what's going on? I've got quite a lot of clever stuff going on here, but I'm not going to dwell on too much of it. Go's got a really nice switch statement that's very, very similar to the case statements in Ruby, in the sense that every single case is itself evaluatable. So and you have to, in Go, you have to explicitly fall through to the next case, unlike in C, where you just naturally drop through and have to prevent yourself. Little things like that make it a much safer language for systems programming than C. But anyway, skip on to, before we skip on, will it go? Yes, it is. Also up here, this thing buffer, if you remember, buffer was defined as a slice of integers. And all constants in Go are ideal. That means at compile time, the compiler will work out whether they're ints, floats, or whatever, without you having to specify what they are very often. And this is basically just how you would create a vector type that happens to contain a buffer type that happens to be a slice of those numbers. So it's quite similar to the way in which you would just declare arrays in Ruby, but with a bit of extra boilerplate in there. So file one. To run tests, you have to have a makefile. This is something that's going out of the language, hopefully over the next few months. But at present, all of Go's toolchain relies on you writing makefiles, and they're unnecessary, really. So skip on. Now, this is a slightly more complicated example, because this is benchmarking. GoTest provides you with benchmarking out of the box, but it's got a very strange way of doing it. Completely not the way that Ryan has implemented benchmarking in Minitest. So, Rob Pike's of the opinion that you only really need to know in benchmarks whether something runs for less than a second or not. So, and this down here, this variable n, is actually defined in the benchmarking library. It tries running each benchmark with that set to 1. If it gets a stupidly small number, then it just tries to run it until the machine falls over and cuts the test at a second. And if it gets a number bigger than a second, it says that's the answer, that's the benchmark. And I tend to write benchmarks for nearly everything because it's quite good fun seeing that function call takes 2 nanoseconds on average and things like that. It's a very high-resolution benchmark library. File one. And this is just what it looks like when you are at the console and you run it. Let's see. Next. All right. One of the perennial arguments in the Go community, constant argument, in fact, is Go doesn't have exceptions. There is, I mean, in Ruby we use exceptions all the time. They're great fun. For anybody who's in Avi's talk, I mean, exceptions are great fun. But Go doesn't have an exception mechanism, except that's not really true. Right, next one. This basically is all you need to know to, say, implement catch and throw. Catch and throw is very simple to implement in Go, because Go's got first-class functions, which happen to be, well, they're closures. And on top of that, it's also got a defer mechanism, which will call that thing as it unwinds the stack. So in this case, I mean, at the top, I'm throwing a panic. I'm just saying, this system should die now. And I'm doing it with a nil value, because obviously, I don't want to send information. I just want to get back to the first thing that's willing to catch a throw. I'm not sure this would be safe in real-world code. But, and a catch is quite fascinating, because you have this deferred function, and then you call the function that you might want to catch. And then it calls whatever and ever and ever, and you build a stack tree. And when it comes back up on the way out, you just ask it, am I recovering from something? Have I got something that's been passed back up the stack I should care about? And in this case, I check to see if it's nil. And if it's not nil, which means it's a genuine panic by something in the runtime, I chuck it back up again. But otherwise, I just say, OK, fine. Cut the stack unwind there. Let's just get on with what we're doing. So catch-all is just that taken one step further. Throws panic is actually quite a useful little testing thing, because there's no built-in support in gotest for saying, did this thing panic or not? But there doesn't have to be, because, I mean, it's like 7 or 8 lines of code. And the fascinating thing here, of course, is I'm passing in a function, but the deferred function there is itself a closure. So where I set b equals true there, if I get some value come out for recover, that actually changes the return value that comes out of that function. So it's nice. It's sort of, it's very Lispy in those ways. Next. It never used to have all of these pretty red bits. I put them in because when you're trying to present the kind of sessions that I do over a Skype phone call with no video, the thought of trying to say to people, well, look, I'm pointing at this right now when there were 361 slides when I was giving it. I was like, that's not going to work, is it? So, OK, follow on to the next one. Now this is how to implement a stack dump. So I'm going to go through this one in quite a bit of detail because it gets into some bits that I don't play with anywhere else in this presentation. But firstly, amongst the standard packages, there's a runtime package that allows you to actually introspect the runtime. And there's this nice little function called callers that will figure out all of the callers to the function that you're currently in, given a stack pointer. It will just give you back a whole pile of addresses for where those function entry points are. And you can, if you want, actually just recall them, which I haven't demonstrated here. That would be 2 slides rather than 1. But here, all I'm doing is I say, well, I know what these program counters are. Can you tell me if this was a function? If it was a function, can you tell me what line in a source file it was? And then I'll just print that information out. So I'll get my stack dump. And it's very easy to sort of build all of this instrument, your programs at runtime, to do all kinds of clever stuff based on error conditions that would be easy to do in Ruby as well, but would be very difficult to do in, say, C++ or Java. So we'll skip on. Oh, one other thing I want to say before that. Up here, this for clause. For is the only loop construct that exists in Go. And in this case, because I've got a slice of information, it understands that it can give me each item in the slice in turn. So it's a sort of a 4-persons enumerator. Skip on. This is the stuff I spend most of my time actually talking to people about, because I seem to be the only person who's actually obsessed with the reflection system in Go. Yeah. 5 on. Yeah. OK. This lovely bit of code here is how you allocate a piece of memory knowing a particular object that already exists. You can allocate another one that's like it. And this took me about 2 months to figure out because the reflection system was a moving target for most of last year. And it just basically, all that this is doing is giving me a way of being able to create either slices or maps at runtime without knowing what type of slice or map they are before that code path is entered. Trying to do this in C would be impossible without doing an awful lot of very horrible gerrymandering that has nothing to do with the actual implementation of C's binary interface.
You can do this sort of stuff in Java, but it's very, very slow. And it's moderately slow in Go. So this is an example of then testing that out. As you can see, I'm using the throws panic function that I defined earlier, just to see whether or not it will work, and if it won't work, to say this should work, it doesn't. So, fire on. Duplicate's a little more interesting, because I had an actual thing I was working on where I needed to be able to duplicate an existing item, but I didn't want to have to write the code for all of the 13 basic types existing in Go, and then to have to keep re-implementing it for every other type. And Go doesn't have any kind of generics mechanism, so the only way to attack that is to use reflection. So this will quite happily figure out, it will create a buffer using the previous allocate function, and then it will figure out exactly how to squirt data from one buffer into another to copy across your data without caring about what the type is. Quite a lot of these things are slowly making their way into the runtime as generic functions. So we've got a generic copy function and things like that only care that the types match between the parameters. But at the time I wrote this, that didn't actually work for many of the cases I had. So. Yeah. The bit of code I'm going to go into now was considered for some time the most dangerous piece of Go code in existence. And I got an awful lot of very rude comments from people who came from a static typing background about how you should never do this. But sometimes a bit buffer really is just a bit buffer. Sometimes I want to look at raw memory, and I want to do something with that raw memory, and I don't really want to have a type system getting in the way. You don't have use cases for that in day-to-day programming, but I do a lot of work involving virtual machine design. So I'm often trying to curry bits between different types for different purposes. I'm the only person who understands the transform I'm trying to do in that particular context. Yep. And so I created this package called raw. It has, I think it's called random access write is the official name of it. But I release it under a dual license in hopes that somebody will need this for a computer game someday, and would therefore license the closed source version, which is called Read and Weep. Because basically it just, this is the closest to true unsafety that Go can do. What I'm doing here is I'm defining the concept that there's something, that there's an interface called a memory block. And all I care about with a memory block is that whatever object I want to treat as a memory block understands how to create a byte slice. And that is actually a shortcut for a piece of code I'm going to show in a minute. So bear in mind, I'm going to show you some code that's specific to to the reflection system, but at the same time, I'm also going to show a shortcut that allows you as the person using the library to implement your own way of doing it that's more efficient for your actual runtime type. So, for example, if I have a string of 32-bit floating point array of 32-bit floating point numbers, and I decide I want to do this, the reflection system will take about 1,000 times longer to run the code for doing it than if I just write my own byte slice of the 32-bit floating point numbers. So, and we're going to play with, we're going to see something that's core to the way in which Go handles both slices and strings, and that's the concept of a slice header or a string header. These are actually obscured in the language itself. You only ever see this thing as a reference to the underlying data, but the reflection system allows you to treat them as first-class types in their own right. So fire away. There are several interesting idioms going on here. Firstly, you'll notice there are multiple return values. Go is a language that allows for multiple return values. That was kind of an idea that was sexy to me, sort of like in the early 90s when languages didn't have early multiple return values. But it's not really very exciting in the modern world. But it's a selling point to some people, I understand. More interesting is this up here. The second line is actually a type switch. And it's an example of how to do a type switch with reflection as opposed to do a direct type switch. Normally in Go, you would have whatever your variable is, and then you'd have dot bracket and type in there. And then you could use cases that were each of the actual runtime types that you knew about. But with reflection, instead, you ask what the actual kind of the thing is, and it comes back with whether it's a slice or an interface. And all I'm really doing there is I'm creating a new slice header. I'm saying, well, I understand that this slice already exists, so I'm going to create a new header that's got the pointer in it and everything that I can manipulate. And then this thing up here, unsafe pointer, it looks like it's a function call, but actually that's an instruction to the compiler that says, by the way, turn off type checking in this portion. Allow this pointer to point to anything that I ask it to later. So, try one. And this is, well, I thought this was a thing of beauty when I wrote it. This is true of nearly every piece of code I've ever written. I thought it was a thing of beauty at the time I wrote it. I'd apologize to the whole world for this. But basically, this beauty just says, there are two known cases in which I know I do not have to use reflection to create a byte slice from any arbitrary type that comes in. If it actually is a slice of bytes, I don't have to do it. And also, if it complies with the interface I already defined, memory block. Now that means that, because Go's got a bounded package scheme where you can only see stuff inside your package unless it's exported, that would make it, you'd have the same problems you have as in Java, where you can't retrofit functions on without explicitly saying so. Well, doing it this way, any person on the planet who wants to implement a byte slice method for whatever purpose, probably for a legitimate purpose, like turning some string into a slice of bytes, I can now reuse their work whenever that type is chucked into this library by any program without anybody having to tell anything to do it. So that's where type inference starts to feel a lot more like Ruby. So yeah, the most dangerous thing here. Oh, this is it. I love this. On the previous, skip back to the previous slide for a second. Oops, if it will do it. Sorry, there's a lot of slides there, and they've got auto timers in them, and it's all very stupid. On the previous slide, I actually found out what a byte slice was with a one-liner in which I just asked at runtime what the type of a slice of byte is. With that piece of information, which is just a 32-bit number, so you could stick any 32-bit number in there, in theory, although there's only a finite set of types that would be understood by the runtime. I can now just say, you remember that header that I had? Well, pretend that header is a byte slice, create something that would be appropriate for a byte slice. Oh, and by the way, because I need the runtime signature to match to fire it out, just change the type so it really is a slice of byte. And then return it. This is a really stupid example, because actually I can't really think of anybody other than me who would want this piece of code the way it is. But it means that for other purposes, there are purposes in all kinds of low-level operating system stuff where you would want this. I mean, I've seen an awful lot of C code when I used to work at that level that basically was trying to do this through void pointers, which just takes away every type guarantee completely in the entire code path. All right, next one. That's a valid line of Go. That's my defense. This is, well, the Go statement itself is how you launch off a Go routine. And the Go routine is a self-scheduling coroutine that blocks on I/O and moves to a new thread when it's blocking, so that it doesn't block the rest of your program. They're very, very cheap because they have a 4K stack because they're built on Plan 9 threads. And this here is a thoroughly valid, completely useless function call. It's got no content in the function body, but it's a valid function call, so I couldn't resist it. And then, of course, I had to put a comment at the end to get the yourself in, or I'd have had to write code, and it would have rolled over the line, and it wouldn't look pretty. So, fire off. This is a very silly example. This is the one with the code in here. Oh no, it's now one of two pieces of code in here I've stolen from other people. This I've stolen from the Go community. There's another one in a minute I've stolen from the Ruby community. This is basically a random number generator. But it's not a random number generator how you might normally think of them. Because this basically, down here, a select statement is basically you can set up a whole pile of different I/O streams, and it will randomly pick which one to look at next until it finds one that has I/O coming in. And it's very random. As a result of that, the easiest way to generate a random string of ones and zeros is to create something called a channel. And channels are basically just pathways between two separate Go routines. And just chuck zeros and ones down the channel. But I don't want to specify myself what the randomness of that is, so I just say, decide for yourself, pick a 0 or 1. which is kind of cool. I mean, when I first saw this bit of code, this was written by a guy called Andrew Gerard, who's one of the Google Go team. And when I saw this bit of code, I thought, why have I never thought doing random numbers that way before? Why do I always sit down and write a Mercian twist or something stupid like that when I could just, so this is actually quite an interesting bit of code. Up here, I then just print out whatever the next value is that's sat on that channel. And this is a blocking channel. This is synchronous I/O that's going on here, because there's no buffer underneath the channel. And so I'm manually polling. Yeah, that may not be how I want my I/O to always work. So next slide. So this is the same thing, but this is an asynchronous. Oops. I didn't mean to put a skip in there. If you can get it back on the next one, I'd appreciate it. A previous one, I'd appreciate it. You may have to stop the presentation at that point, I think. In my defense, there's over 400 slides, so getting all of my timers right is not,
So
that one, we can stick on this one. Right, what we've got going on here, we're creating an asynchronous channel that can hold up to 16 values. So it will slurp 16 at a time out of this down here. And that just means that, obviously, it frees up on the amount of polling you might do. I'm no longer checking on a limit. And then I might do another one where I decided I wasn't even going to ask for 16 numbers out anyway. But anyway, that's all there is to actually doing synchronous and asynchronous I/O in Go. It's exactly like having pipes between processes on a Unix box and just using select calls in that context. Right, next one. Oh, and that 4 at the bottom was just to create an infinite loop. So this takes it a little bit further, because sometimes you might want to actually write other stuff that wants to take a signal source and wait until the signal source is finished. So a signal source, in this sense, is a closure that I've just, said is a type, because you can basically functions, etc. You can bind them as user-defined types as well. All this really does, it just effectively this just implements the equivalent of thread wait. It's not very exciting. So next one. This is all of this example is building towards MapReduce. MapReduce with reflection, so that it's arbitrary MapReduce. So you just have to use the one MapReduce engine. You don't have to keep rewriting it for stuff. And we've got several things going on here. Now, the great thing about having functions as first-class types themselves is that then you can define methods to apply to the function. So that's apply at the top, takes some parameters, and then calls the function itself that is the memory representation of the type to then go off and do the work, and it pumps the value out onto the channel that you pass in as one of the parameters. So it's very, very easy to build filter chains just by defining types and then embedding types inside each other. The each at the bottom is just a really bad way of implementing a Ruby-style iterator. Next. Combination is slightly more interesting because effectively I've just said anything that's got that function signature, takes 2 parameters and gives 1 back, can really be treated as being a reducer. So that's a natural reduce step in a MapReduce pipeline. Down here, you can see that we've got a Go routine. This is a closure. Now, I had an argument with somebody in a meetup in Scotland about this. He was an Erlang fan. This is a closure. This shares state at the point at which it's created with everything before that. It's inheriting all the environment down from before it. That means if I have several of these in parallel, they all share the same state, which is, shared memory. There are actually a lot of problems where that's useful, where you want to share state, but you want to share state in a bounded way, which is the problem really with shared memory in Unix. Most of the implementations aren't that bounded. And what's happening here is this is going off, and it will run a whole load of different iterations and pump a whole pile of values out onto a channel and pull them out. Skip on. A transformation is even simpler, because really a transformation is just taking one value and turning it into another one. So I've just implemented a whole bunch of combinator math theory in like 4 slides, which you could do in Ruby, but you couldn't do in C. And this is the real point of Go, that you no longer have to think to yourself that systems programming means I'm going to spend the next 3 months of my life writing boilerplate. I can actually do systems programming the way I do Ruby programming. So, and for those who really love test-driven development, it even comes with a testing tool. You poor benighted souls. And obviously, the great thing about a transformation is is quite useful as part of a map operation. So we'll skip on from that because that's just doing the same as the previous but with different stuff. And in here you can see there's one really ugly thing with first-class functions. There's no literal type to express them. So you have to always cast a lambda to actually be of the right type that you're trying to use it in. I think this is so ugly. But finding a good syntax for this has actually proved very, very difficult. So it may be a wart that stays there for a long, long time. Skip on. And here's just a little program that basically uses the previous to just go off and compute some sums, and it's not very exciting. Right. Okay, this is basically a piece of code I showed off last year in the concurrency session I did with Elise Huard. And people keep saying, well, you know, Ruby concurrency sucks, and in many ways it does. Global thread locks and things like that. But you can do exactly the same idiom as I just demonstrated in Go in Ruby, because you've already got two tools in the standard Ruby library for doing it. If you import thread, sorry, wrong language, require thread, and use thread local variables, you can just bind atomic queues to threads. So the following bit of code is going to demonstrate that. This is all going to be available online, hopefully when SlideShare stops being pissy about uploading from here. And then you can read all of this. It's actually designed to read offline mostly. Can we skip back a page? Maybe 2 pages. Right, maybe 3. Yeah, oh, maybe 4. It should say thread, that's it. How many people use thread groups? Some. That's good, because to be honest, most times when I ask that question, people say, what are thread groups? Because people just don't seem to use this side of Ruby very much. Sometimes if you've got a group of threads, you want to be able to say, I want to send something to every thread except me that's in the group. And other times you just want to be able to find a particular thread. So all of this is some boilerplate to do that. But the important thing for the example is obviously we're using sockets and threads. Hi, one. It wouldn't be one of my sessions if it didn't do this. All right. Now, the important thing here, I've actually optimized this since I showed this code last year, is all you have to do is when you initialize a thread is bind an atomic queue to a thread variable and just never change the thread variable. And then you've got an atomic queue, which is exactly the same as a channel in Go. So once you've done that, you can then allow people to send messages to the thread in their normal boring code, and then you can quite happily go off and you can enqueue all of those messages, and that's all taken care of under the hood without you having to care about it atomically. So you won't have any sort of race conditions crop up from that. And this bit of code just demonstrates how to then bind an I/O loop to a thread variable, so that now I can send messages to any random piece of I/O that happens to be bound in. I simplified this example slightly because this used to be the default parameter to the method with the actual thread creation. Because I quite like doing things like that at times because it's quite fun. But and it allows you to stick your own I/O handler in if you do it that way. That doesn't necessarily even have to be threaded. So you could sort of use the same pattern with Event Machine or things like that. But for this, it's a bit of a digression from the point, really. And basically, all you then have to have is a loop that's going somewhere that just dequeues items off the queue. And the dequeue is actually a blocking operation. So that thread isn't going to waste processor cycles running a pointless polling loop while it's waiting for things to come in. And it just shuts it out on a socket. And I quite like just closing sockets in the places where I actually use them. So, right, next one. This is a chat server. I'm not going to talk about the code in any great detail, except that I've got 3 thread groups, which means I can move a connection between being a receiver, a transmitter, or deceased. Or I can have a deceased transmitter or a transmitter that's a receiver, for example. And obviously, you have to register things up, and you have to pass stuff about. It's very unexciting. Skip. Oh, it's got a typo. That's not a bracket where it shouldn't have been. The important thing with this is actually having a run method, because otherwise you're never going to launch the thread that's the actual background listening thread that manages the thread groups to take the other threads that do the I/O. And obviously some cleanup. Right, file. Okay, how are we doing for time?
The next talk is supposed to start in
Oh, you're
10 minutes.
reading my mind, aren't you? All right, well, good artists imitate, great artists steal ridiculously and Borg-like. Go doesn't really aim to displace C from the world of programming. It's just nobody who's ever programmed in Go would ever want to touch C again. But we need to live in a world that's got C libraries. And Go is statically compiled and statically bound. So we've got some problems about how we can actually interface with those C libraries. So, fire off. We've got a tool called CGO. And CGO can allow you to bind in any dynamic shared library on your system. And then you can just wrap it up in a way that's very Go-like. Next. The make file back there was necessary but boring. This is from a project I've got going on because I started out to write my own SQLite 3 wrapper because I didn't like any of the 3 that existed. And then I ended up apparently taking all of them and rewriting all of them as well, and then somebody decided they would make it public, which I'm still not happy about because people might actually use this code in a reliable setting, which was never the intent. What we've got going on here, we've got a fake package called C that doesn't really exist. And only the CGO tool understands that. And we can put any number of C statements in the preceding comment before that statement, and it will quite happily compile them into your code when it's compiling up to be able to use the library. In this case, I don't really have to do anything except include the header. You can actually get at C types directly by saying that they are C types, that they're part of the C package. But you're only ever supposed to access them via pointers for obscure reasons that I often forget about and ignore. It doesn't seem to be a problem with basic types, but pointers to big things go a bit funny at times. I think it's an alignment issue. And down here, we've got some error handling, because I don't normally talk about error handling, because I don't like Go's standard error handling idiom, which is to return an OS error value. But it's low-level code. You sometimes have to return errors. Next page. But what we've got going on over here is I've defined some constants. Those constants all exist in the SQLite library, but they're all a bunch of defines, and the defines don't turn up in your Go code, which is something that has to be improved on, I think, before this is really going to be a major commercial success at all. But you've got some fun things you can do. I mean, there's a map with some text. And this is how the standard error idiom is that you define a string method on your error values, and then they automatically will print themselves out in format statements when you want to print stuff. Next page. This is where it gets a bit more interesting, because here I'm currying together, well, currying isn't quite the right word, but I'm messing around with some C strings to turn Go's idea of strings, which are UTF-8, into C's idea of strings, so I can sort of open files by file name and so forth. And you can see these statements here. These are all C function calls that are in line and are able to access variables that I've already defined are compatible with C as part of the structure, etc. Next one. And over here, you can see I can use Go's error recovery panic recovery mechanism just the same way I would in a normal Go program to recover from errors in C programs. Next one. And here's just as, there's a header missing there that should have come up first. But anyway, this is not code that works, because it turns out I don't have ruby.h on my MacBook, because my MacBook is not my normal Ruby development machine. But this is basically how, more or less, how you would load the Ruby interpreter into a Go program so as to then drive Ruby from Go. So, skip on. Yes, that's just an example of what it would actually look like passing in Ruby code with the normal C API stuff. Next slide. There's some homework that goes with this. I was talking to Evan last night about whether Rubinius really is embeddable as just a standard C library, and apparently it isn't yet because they want a clean API, and you know the sort of thing. It will never happen because we don't care, because nobody ever does it anyway. But I would recommend that if you want to find out how CGO works, a great project would be to go off and test how to actually get Ruby loaded into a Go program, because it will be hard work. It's quite a substantial API. Skip on. And this is where you can find out more. Golang.org is where you can get the language. #Golang is where everybody hangs out on Twitter. That Pledgy account is where you can help keep me unemployed for another year so that I can work on this mad stuff. I've got some projects on GitHub. For somebody with such a long history in the Ruby world, hardly any of them have anything Ruby related because all of my Ruby code turns up in talks normally. But I've got some actual useful stuff for Go. And the slides are available there, which is actually SlideShare, so it will have reasonable download bandwidth. There's about 406 of them for this, but that's because of the color coding. So I think it's about 70 in reality. But anyway, if you want to find out more about Go, then quite happily come and corner me with beer. And I finished before the next one's going to go on. In fact, 45 minutes and 10 seconds, I think, is the fastest I've ever delivered this. So thank you very much for your time, and go hack.